For more than half a century, astronomers have used one basic rule to weigh galaxies they can barely see. Look at the bright stars. Estimate how many faint stars must be hiding underneath them. Add everything together. The method works because astronomers have generally assumed that stars are born in roughly the same proportions everywhere. If a cloud creates a certain number of massive stars, there should be a predictable population of smaller stars accompanying them. But Gaia has now given researchers a way to test that assumption directly. After examining star clusters across the Milky Way, astronomers found that different clusters appear to have been born with genuinely different distributions of stellar masses. The cosmic rule used to infer the invisible stars inside distant galaxies may not be universal after all, and that could matter enormously for James Webb observations. Some galaxies in the early universe have appeared surprisingly massive. The usual interpretation is that they somehow formed enormous numbers of stars extremely quickly, but there is another possibility. Maybe part of the mystery comes from the ruler astronomers have been using to weigh them. That ruler is called the Stellar Initial Mass Function, or IMF. Imagine forming 1,000 stars inside a giant molecular cloud. Some will be enormous blue stars, dozens of times more massive than the Sun. Many more will be small red dwarfs containing only a fraction of the Sun's mass. The IMF describes that distribution. It tells astronomers how many stars should be born at different masses. This sounds like a technical detail, but the IMF sits underneath a huge amount of modern astronomy. Massive stars are extremely bright, while small stars are faint. In distant galaxies, telescopes can detect the combined light of the stellar population, but they cannot count every individual red dwarf. Astronomers therefore use the visible light to infer the population they cannot see. It is like looking at the lights of a distant city at night and trying to estimate how many people live there. If you know the typical relationship between bright office towers and ordinary houses, the lights give you a reasonable estimate. But imagine discovering that every city builds completely different proportions of towers and houses. Suddenly, the brightness is no longer a universal measure of population. That is approximately the problem astronomers may now face. For decades, researchers knew from theory that the IMF could depend on the environment where stars form. Temperature, chemical composition, gas density, and turbulence can all change how a molecular cloud fragments before collapsing into stars. But actually proving that the IMF varies has been difficult. The biggest problem is time. A star cluster today does not contain exactly the same population it had when it was born. Massive stars live fast and die young. The heaviest stars may disappear as supernovae after only millions of years. Low-mass stars face a different fate. Gravitational interactions can gradually throw some of them out of their original clusters. So if two old clusters contain different proportions of stars today, that does not automatically mean they were born differently. Evolution may have changed them. The new study attacked this problem using a particular feature of the mass distribution known as the break mass. A common way to describe the IMF is with a broken power law. Below a certain stellar mass, the number of stars changes with mass at one rate. Above that point, it follows another. The point where those two regimes meet is the break mass. The researchers modeled how star clusters evolve and found something useful. As stars die or escape, the slopes of the observed mass distribution can change dramatically. But the break mass remains comparatively stable. That means the break mass can preserve information about the original population even after a cluster has evolved for millions or billions of years. This gave astronomers something close to a fossil record of star formation. Then Gaia made the measurement possible. The European Space Agency's Gaia mission has mapped the positions and motions of more than 2 billion stars with extraordinary precision. That allows researchers to determine which stars belong to the same clusters and measure their properties far more reliably than previous surveys could. The team began with a catalog containing 7,167 Milky Way star clusters. Most could not be used. Some lacked enough stars. Others had measurements that were not precise enough to reliably determine the break mass. After applying strict quality requirements, only 110 clusters remained. That smaller sample was enough. If the IMF were truly universal, the clusters should have shared approximately the same break mass once observational uncertainty was considered. They did not. The break masses differed substantially from cluster to cluster. Because the researchers' modeling indicated that ordinary stellar evolution should not create those differences, they concluded that the clusters had formed with different initial mass functions. The most interesting pattern involved age. Older clusters tended to preserve different characteristic masses from younger ones. The researchers interpret this not as age physically changing the IMF after formation, but as evidence that the average conditions inside Milky Way star-forming clouds have changed over cosmic time. A cloud producing stars billions of years ago was not necessarily operating under the same conditions as a cloud producing stars today. This is where a study of nearby stars suddenly becomes a study of distant galaxies. When James Webb observes a galaxy more than 13 billion light-years away, it sees that galaxy when the universe was young. Astronomers measure its light and use models to determine how many stars it contains and how massive those stars are collectively. Those models normally require an IMF. Use one IMF and you get one estimate for the galaxy's stellar mass. Change the assumed proportion of massive and low-mass stars, and the answer changes. A galaxy containing proportionally more luminous massive stars can produce much more light for the same total stellar mass. That means a distant galaxy could appear astonishingly massive when analyzed using the wrong stellar population model. The University of Missouri researchers specifically note that an environmentally varying IMF could help explain why some JWST galaxies have seemed more massive than expected. This does not mean the mysterious early galaxies have now been explained. JWST has revealed a complicated early universe, and galaxy masses depend on far more than one assumption. Dust, star formation history, chemical composition, active black holes, and uncertainties in stellar evolution can all influence the interpretation of their light. The new research instead removes one piece of apparent simplicity. Astronomers can no longer automatically assume that the stellar population observed around the Sun provides the perfect template for every galaxy across cosmic history. That has consequences beyond mass. Massive stars dominate ultraviolet light and rapidly enrich galaxies with heavier elements when they die. They also produce supernovae, stellar winds, and radiation capable of reshaping surrounding gas. Small stars contribute much less light but can survive for tens or hundreds of billions of years. Change their relative abundance and you change how a galaxy evolves. A population unusually rich in massive stars would recycle material quickly, produce more supernovae, and generate intense radiation. A population dominated more strongly by low-mass stars would lock much more material into faint, long-lived stellar bodies. The IMF therefore affects estimates of star formation rates, chemical enrichment, and the history researchers reconstruct from galaxy observations. The result also explains why proving IMF variation has been such a major goal. Astronomers were never certain that nature had to use one universal distribution. The convenience came from measurement. For distant galaxies, individual faint stars cannot be resolved, so scientists needed some distribution to put into their models. The Milky Way provided the best tested option. What began as a practical assumption gradually became one of astronomy's most widely used standards. Gaia has now made it possible to test that standard using the stars close enough for us to count individually. But there is an important limitation. The 110 clusters all belong to the Milky Way. Researchers have found variation inside our galaxy, but that does not tell us the exact IMF of a galaxy observed only a few 100 million years after the Big Bang. Early galaxies could contain much hotter gas, lower concentrations of heavy elements, and dramatically different star formation conditions. So astronomers cannot simply replace the old universal IMF with one new universal formula. The researchers argue for something more complicated, an IMF that changes according to the physical environment that creates the next challenge. Scientists now need to work out which environmental properties determine the stellar mass distribution strongly enough to build predictive models. Cloud temperature is one candidate. Metallicity, the abundance of elements heavier than hydrogen and helium, may also matter because it affects how efficiently gas cools. Density, pressure, turbulence, and radiation could all influence how a molecular cloud breaks into smaller fragments. If researchers can connect those conditions to the resulting IMF, they may eventually look at a distant galaxy, estimate its star-forming environment, and choose an appropriate stellar distribution instead of blindly using the Milky Ways. That would turn the IMF from a fixed cosmic rule into an environmental measurement. And that could change how some of the biggest surprises from JWST are interpreted. A galaxy that seems impossibly heavy might remain genuinely extraordinary, or some of its apparent mass could disappear once astronomers realize it produced a different mixture of stars. Either result would be useful. If the galaxies remain too massive after better stellar models are applied, the challenge to galaxy formation theory becomes stronger. If their estimated masses decrease, then at least part of the mystery was not new cosmology. It was a calibration problem. This is one of the strange things about astronomy. Scientists cannot place a distant galaxy on a scale. They cannot collect every star and add its mass. Almost everything we know about these objects comes from interpreting light. Every interpretation, therefore, contains assumptions. Usually those assumptions are invisible until better observations finally allow someone to test them. Gaia did exactly that. It did not discover a new particle or photograph an unknown object. Instead, it examined ordinary stars inside our own galaxy closely enough to challenge the rule astronomers use to interpret galaxies across the universe. For decades, the same stellar recipe was applied almost everywhere. Now 110 clusters in the Milky Way suggest nature does not always follow that recipe. And some of the distant galaxies that seem to be breaking our models may have been telling us something simpler. Before rewriting the universe, we may first need to fix the ruler we use to measure it.